For as long as humanity has gazed up at the night sky, we have been captivated by a single profound question. It is a question that has echoed through the halls of philosophy, inspired countless tales of science fiction, and driven our scientific exploration of the cosmos. Are we alone in this vast, unending universe? The sheer scale of the universe, with its billions of galaxies, each containing billions of stars, suggests that the odds of Earth being the only cradle of life are infinitesimally small. We have sent rovers to trundle across the dusty ochre landscapes of Mars, searching for the faintest chemical traces of past or present life. Our space probes have swooped past the icy moons of Jupiter and Saturn, where vast liquid water oceans might lie hidden beneath frozen shells. Yet, despite our best efforts and our most advanced technology, the universe has remained stubbornly silent. The SETI project has listened for decades to the cosmic static, hoping to catch a deliberate signal from another civilization, but has so far heard nothing. Our probes have found tantalizing hints of habitable conditions, but no definitive proof of life, not even a single microbe. This cosmic silence has led some of the most brilliant minds on our planet to ponder a different, more audacious question. What if, instead of just searching for life, we could actively seed it? To even begin to contemplate such a monumental undertaking, we must turn to one of the most revolutionary and rapidly advancing fields in modern science, synthetic biology. This is not biology as we have traditionally known it. Instead, synthetic biology is about designing and constructing new biological parts, devices, and systems. It is about taking the fundamental building blocks of life, DNA, proteins, and cells, and reassembling them in novel ways. In essence, it is the engineering of life itself, treating the genetic code as a programmable language. The journey from theory to reality is marked by several groundbreaking achievements, but one stands out as a true watershed moment. This was the creation of the first self-replicating synthetic bacterial cell in 2010. For the first time in history, a living organism was functioning and reproducing under the complete control of a genome that had been designed in a computer and assembled chemically in a laboratory. The process began not in a wet lab with test tubes, but in front of a computer screen, where they carefully edited the digital genetic code. When this new cell divided, it passed on the synthetic DNA to its offspring. It was alive. A new synthetically derived life form had been created on Earth. Engineering life for another world is not simply a case of transplanting Earth microbes and hoping for the best. The conditions on a world like Mars are so profoundly different that terrestrial organisms would perish in an instant. Therefore, our synthetic life would need to be redesigned from the ground up, equipped with new abilities borrowed from the hardiest organisms on our planet, the extremophiles. We could equip our synthetic microbes with genes from bacteria like Deinococcus radiodurans, which can withstand radiation doses thousands of times greater than what would kill a human. For extreme cold, we could borrow genes from Arctic fish, which produce natural anti-freeze proteins that prevent ice crystal formation. The colonization of an alien world would begin with a pioneer species. On Mars, this means tackling the soil, which is rich in perchlorates, toxic salts harmful to most known forms of life. Our first synthetic organism would need to be a perchlorate eater. As these microbes consume the toxins, they would release harmless chloride and, crucially, oxygen. We might envision robotic rovers or aerial drones scattering vast quantities of these dormant freeze-dried microbes across wide swathes of the Martian landscape. We would target areas known to have subsurface ice, which could provide necessary water when it sublimates into the atmosphere. As we stand on the cusp of being able to engineer life for other worlds, we must pause and confront the profound ethical questions that this power entails. The ability to create life and place it on another planet is a power of cosmic significance. By what authority do we appoint ourselves as the architects of a new genesis on a world that is not our own? For decades, our space exploration has been guided by strict planetary protection policies, avoiding contamination of other worlds with terrestrial microbes. But what if a world like Mars harbors its own native microbial life, hidden deep beneath the surface? Our robust engineered organisms could outcompete and drive this native life to extinction before we ever had the chance to discover it. The most ambitious application is terraforming, the process of deliberately engineering a planet's environment to make it more Earth-like and habitable for humans. Our pioneer organisms would begin this process. We could engineer them to produce potent greenhouse gases, initiating a feedback loop that would gradually warm the planet. Over centuries or millennia, this biological process could transform the Martian climate, raising atmospheric pressure and temperature until liquid water could be stable on the surface. This is a vision of humanity as cosmic gardeners on the grandest possible scale, offering the promise of a second home for our species. Beyond terraforming, synthetic life offers vital practical applications. Imagine an astronaut on Mars developing a medical condition. Rather than needing a massive pharmacy, they could have a bioreactor filled with engineered organisms. Upon diagnosis, they could simply add a specific chemical signal to the culture, instructing it to produce the exact antibiotic, painkiller, or vitamin they require. We could design bacteria that secrete biological cement, allowing us to mix them with Martian regolith to create strong, durable bricks for building habitats. This living concrete could even be self-healing. If a crack forms, dormant bacteria within could sense the exposure and begin secreting new cement to fill the gap. Creating a single pioneer organism is challenging, but the ultimate goal is establishing a functioning, self-sustaining ecosystem with multiple synthetic species working together. However, building an ecosystem from scratch is like constructing an intricate house of cards. If one key organism fails, the entire system could come crashing down. We would need to implement kill switches, genetic circuits that would cause organisms to self-destruct if they begin to behave in unintended or dangerous ways. Even with precautions, the risk of catastrophic failure remains high. Establishing the first alien ecosystem will be a delicate, high-stakes balancing act. We now find ourselves standing at a profound threshold in the history of our species, and perhaps in the history of life itself. The capabilities being forged by synthetic biology represent a fundamental shift in our power over nature, granting us the tools to move from being observers of life's story to becoming its co-authors. The prospect of engineering life for Mars or beyond is a testament to human ingenuity and our unyielding desire to explore. The successful creation of synthetic organisms on Earth has proven that life is, in essence, a programmable system. The story of evolution on Earth is a 4-billion-year epic of chance and necessity. The advent of synthetic biology allows us to contemplate writing a new and entirely different chapter. By designing life for another world, we would be initiating a second independent line of evolution, a process kick-started by human intelligence. What kind of creatures might eventually emerge? The lower gravity, thin atmosphere, and unique chemistry would all sculpt life in novel ways. By establishing a second self-sustaining biosphere, we ensure that the phenomenon of life is more robust and resilient. The journey to engineering alien life cannot be undertaken by scientists in isolation. This is a conversation that must involve everyone, philosophers, ethicists, and the public. The decision to alter the biological state of another world is a choice that will define our species for generations to come. It is a choice that balances the profound allure of creation and expansion against the solemn duty of preservation and respect. As we look up at the night sky, at the pinpricks of light that represent other suns and other worlds, our perspective is changing. We are no longer just looking for neighbors, we are contemplating becoming pioneers. We are at the dawn of a potential new genesis, one designed in our labs and launched from our world. The shocking truth is that this power is nearly within our grasp, and we must now decide if and how we will ever choose to use it. The silence of the universe is now also a canvas upon which we could paint a new masterpiece of biology. We would be transforming life from a local phenomenon into a galactic one, starting the next great chapter in its cosmic journey, a chapter that is, for now, completely unwritten.